Okay, so the natural extension of the discussion of weathering and erosion is soil development. And so rocks weather in high relief, high, in the mountains essentially, or at high altitudes, and then they're transported, both, the physical and chemical breakdown products of that weathering is transported across the continents until eventually it makes it to the ocean, most of it. But all the while, there is soil development taking place. And so soil development really kind of looks like this. At some point, you encounter fresh bedrock, right? But just above that, it grades. There's kind of this gradational transition into something that looks like weathered bedrock. And then moving up, you go through some soil horizons until eventually at the surface you have something that looks like soil, right? Um, and so it at the surface, the soil is characterized this A horizon by a lot of what we call humic substances. Those are really just decomposing organic material, and because of that decomposition, there's a lot of CO2 released to the environment, right? Because of respiration, and there's also a lot of nutrients being re-released to the environment. And so this surface soil is organic rich. It's pretty nutrient rich, and in general, it's fairly acidic, oftentimes because of that respiration, right? Because of that, there's a whole bunch of stuff that leaches out that's soluble in acidic solutions. And so as water kind of percolates downward, it dissolves a lot of things in the A horizon. And then the B horizon is characterized by low organic matter, and really the accumulation of let's see, can't see my mouse there. Now you can see my mouse. Really the accumulation of a lot of those dissolved products. They reprecipitate in that B horizon. But in general, you're going to have some zonation to soils. They can be well developed or poorly developed for a variety of reasons. In high relief areas like the side of a mountain, you might have the exposure of fresh bedrock with no soil, right? And there could be any amount of soil development in between, right? A real soil, the top soil anyway, the A horizon, looks something like this in a kind of well-developed area. Um, if it, a lot of soil development depends on really two things: the climate locally and the relief. So a really high relief area is going to have a lot of erosion, a lot of removal of material, and so you might not have time to develop soils. Whereas a flat area might become highly weathered and deeply eroded, or deeply weathered rather. But a lot of it has to do with the climate. So in kind of a temperate or moist climate, you might get well-developed soils. In a drier climate, you might not get as pronounced development of the horizons. It's not as productive generally. Um, not as much plant biomass is being produced, so there's not as much decay of sedimentary organic material in that A horizon. And you might not have a really strong development of the horizons in general because you don't have a lot of water fluxing through the system. So there's not a lot of chemical weathering taking place. Sorry, my cat is wants attention. In a really wet climate, on the other hand, like the Amazon, for instance, the Amazon rainforest, you have really deep weathering. And I mean deep weathering to say like complete weathering. And so most of the soluble products have been carried away, and most of the minerals have been converted to these very stable oxides and clay minerals. And so this is almost a complete weathering of the available material. And as a result, it actually becomes pretty, if you think about clay, um, it's really cohesive, it's not very permeable, and so it doesn't actually accumulate very much organic material. And so it can become, yeah, a very deeply weathered soil. And there are some names we applied to those later on, like an altisol, meaning the sort of ultimate product of weathering. In any case, so limited time, like a high slope, a high angle slope can lead to poor soil development, something like this. Um, Limited water can lead to a poor soil development. Um, this is a good, kind of a semi-arid environment will lead to development of good horizons. You can really see the layering, and you can tell compositionally different. They're compositionally different. Um, let's see. So these are a couple of other kind of decently developed soils, just different ones. This is aluminum or iron-rich soil. This isn't particularly well developed here, but these are the ones I was talking about. This altisol or an oxisol refers to the presence of lots of oxides, and you can see they're really homogeneous. They're very red, indicating the presence of a lot of iron oxide, rust essentially. Right, but there's not very good development of horizons, and that's really the result of extensive weathering and the development of clay minerals. And so a lot of this has to do with climate and local topography, local source rocks for weathering, things like that. And so this is just a map of soil heterogeneity across the U.S. Soil erosion or degradation more generally is a really big deal. It's really important to prevent it because soils take a really long time to develop, and we're destroying them at a kind of an alarming pace. A lot of different things can lead to soil degradation or erosion. Irrigation, this slide says irrigation can help stabilize soils, certainly stabilize them from the wind if we're growing crops, but if you irrigate too much and you allow it to dry without flushing the soil out regularly, you can end up precipitating a lot of salt, and that can lead to conditions that are not good for plant growth. So that can really degrade soil. So generally, when you're farming, you need to regularly flush the fields. Wait, my cat's gonna start yelling at me. There are really two physical processes that are going to lead to extensive soil erosion: wind and water, right? And so these are examples of dust storms carrying sediments away, and this is these pictures kind of capture extensive, particle transport anyway. A lot of mud that's coming from soils out of the mouth of a river, and putting soil into waterways can lead to a lot of undesirable outcomes like algal blooms and other really less than desirable conditions. There are a variety of causes of soil degradation. In particular, urbanization and deforestation are huge. Overgrazing is really a big deal as well. Not to say that these aren't. Desertification captures kind of a lot of these issues. And soils just can generally degrade. This is a problem, especially because our population continues to rise, and we need farmable land to grow crops to feed people. This last kind of slide captures the progression, recent progression of soil degradation and erosion. Deterioration is the word that they're using here. Overgrazing contributed about 35% of this. This is from 1992, it appears. So these numbers may have changed quite dramatically, but at that point, I would imagine they haven't changed that much. At that point, about 35% of soil erosion was caused by overgrazing, 30% due to deforestation, 28% due to just poor agricultural practices, and 7% was other causes, both natural and human. So even less than 7% of soil erosion and deterioration is due to natural causes, whereas we're causing a lot of it. So it's a big issue. But in general, right, I really just want you guys to have this kind of holistic notion of rocks are uplifted through tectonics. They break down physically, they dissolve chemically. The products of that, the smaller bits of rock, progressively smaller and smaller, and the dissolved products are transported across land, and eventually they end up in the ocean. As they're being transported across land, soils develop. The soils really act to provide a substrate for plants to grow, right? And so they act to kind of meter the transport of nutrients, or kind of slow down nutrient transport out to the oceans, and make those nutrients available for photosynthetic productivity in terrestrial environments. But yeah, it's you know, this kind of whole system that it fits within. And so we go from this into the carbon cycle. I think is the next. Yeah, because we didn't get to groundwater until after that. So this goes directly into the carbon cycle, which is really logically the next place to go, as this obviously has major implications for both the short-term carbon cycle, you know, the biosphere, and also for the long-term carbon cycle, right? The long-term carbon cycle is all about what chemical weathering and turning atmospheric CO2 into limestone eventually. And so we'll get into that next.